The distribution of sample means. This histogram is showing the distribution of heights for a population of students. There's actually a few thousand students represented on this. We have their heights on the horizontal axis in meters and frequency on the vertical axis. I'm going to randomly select 30 students from this population. The arrows here indicate some students that have been randomly selected. The mean height of those students has been calculated and it's plotted as this little box here. And now I've taken a second random sample of 30 students, worked out the mean of those students and plotted their mean height as well. So now we can see two means there. There's a little box there and another one here. And if I repeat the process, so each time I'm selecting a random sample of 30 students, I work out their mean height and I plot the mean height on this graph. If I speed things up, I get something like this. So just to go over that process again, here's the histogram again, and I've taken a sample of size 30 each time, and I've worked out the mean each time. The arrows represent some students randomly selected, and there's a mean right there. And if you repeat that many times, you'll see the distribution in the middle is for these sample means. The curve in red is for the underlying histogram, and we can see we have a normal distributed population of student heights, and the curve in black is again normally distributed. It's for the sample means and it follows this distribution, and they are similar. You can see the means are identical, but the spread in the distributions differs, and you can just tell that from the shape of each distribution. The sample mean distribution has a reduced variance or standard deviation, so we have a new variance and it's always sigma squared over n. So you take the variance of the underlying population, this one, and you divide it by the sample size that we were taking each time, which was 30 in the example that I just did. So it would be that variance divided by 30. This value here, this fraction, is the new variance, and it's the variance for the sample mean. So the underlying population, so the heights of all the students, as we just looked at, so we've got x, the heights of students, the random variable. And a typical question might be, if we randomly select a student, what's the probability that the student's height is less than 1.90 meters? Once we've taken a sample, and now we're looking at the sample mean distribution, which was this one, any calculations we do for this distribution will have probability, and it has to have x bar. We're looking at sample means. It's no longer x, it's x bar, and we have to use this variance in any calculations instead of this one. So again, in the underlying population of student heights, we have a mean, a variance and standard deviation. If we take a random sample of size n, and now we're looking at the distribution of the sample mean heights of the students, so this time we've got the same mean, so that distribution there has exactly the same mean as the underlying distribution. The variance you modify, you take this variance, you divide it by whatever your sample size was, so this is the variance of this distribution, and then for standard deviation we know we square root the variance, so we get this. For calculations involving the normal distribution and standardizing, this is the formula that we use, and there's a reason I put SD there, standard deviation, rather than just putting the Greek letter sigma there, because the standard deviation here and here are not the same. So if I substitute these into our formulae, we get these. So to answer a question like this, x, this standardizing formula, and if it's got x bar as sample mean, then you use this formula for standardizing.